Hello, my name is Shiven Parikh, and I'm in the 10th grade at the Dayton Regional STEM School. And I'm really interested in cybersecurity. Over the past 2 years, I have explored different cybersecurity topics and fields in the real-world applications. In fact, last year, I did a project on password safety, and I created a brute force password cracker in Python that evaluates the strengths of different passwords. Fortunately, I was given the opportunity to go to the district and state level to showcase my research and inform the audience about the crucial aspect of making passwords. So with that being said, let's get started. Here I have different bills. I have a $5 bill, a $20 bill, and a $50 bill. My question to you is, what are some ways I can test the authenticity of these bills? Now you may have said different things like the digital watermark, or the feeling, or the serial number, etc. The main one we'll talk about is the digital watermark. Everyone knows that the quickest way to find or check the authenticity of these dollar bills is holding it up to the light to see that digital watermark. If you see a hologram like the past president or like the bill value, you know that the bill is authentic. So like I mentioned earlier, this process is known as a digital watermarking, and it falls under steganography, which is the art of concealing data in physical files and digital files without it being seen through the eye. Another example I have of steganography is shown right here with this image. So does this image look unusual or wonky to you? Most likely not, but how would you feel if I told you that this image actually has a paragraph worth of information in it? Pretty shocking, right? We've all received images in some way or the other, either off the internet, by a friend, or off social media. Therefore, protecting and verifying the credibility of these images becomes crucial due to the concerns around counterfeits, privacy, and authentication. To address this, image steganography has emerged as a technique to conceal data in images without it being perceptible to the human eye. However, a significant struggle that ethical steganographers have is hiding a lot of information or hiding additional information and finding the right balance between information and the risk of image corruption. To investigate this, I evaluated an existing least significant bit method and my proposed least two significant bit method, commonly known as LSB versus L2SB. So what is the main question I'm trying to solve? So the main question I'm trying to solve is, how can I incorporate additional information in images while yet minimizing the risk of image corruption? Now let's take a step back to steganography. Steganography is a branch of cryptography, and cryptography deals with the use of using encryption to render a message incomprehensible. And this is different from steganography because steganography hides the information, while cryptography tries to make it unreadable. So a real-world application is, I open a Word document, type in a couple of sentences in Calibri, font size 11, all the standard, and then highlight one sentence and change the font family or font type to a one with just symbols. So if you were looking over my shoulder, you would see that this person has written something, but you wouldn't be able to fully understand what it means. With steganography, however, you would take that same sentence, and instead of changing the font type, you would change the font color to white, making it completely invisible. So now if you look over my shoulder, you won't even see the sentence. So overall, cryptography conceals the meaning of the data, while steganography conceals the presence of the data. So there are 5 main types of steganography. You have text steganography, video steganography, audio steganography, image steganography, and network steganography. As mentioned earlier in the project, the main for this project is image steganography. There are many ways to hide data in images, but the more prominent one is the least significant bit, or the LSB method. The least significant bit method is based on hiding information in the least significant bits of each byte. So in this diagram, you can see that in the RGB bytes, the ethical steganographers exploit the use of the least bit to hide information. For example, the binary of the lowercase a is 00001110. So now what ethical steganographers would do to completely hide a into an image, what they would take the first bit, which is 0, and go into an image and use the least significant bit algorithm to change the least significant bit from a 1 or a 0, depending on the depending on the value that it already was before and the value that it needs to be changed to. So they would switch it to 0 or 1 or vice versa and continue along that path until A is completely dispersed. So what I want to do is I want to use LSB to make an L2SB. So instead of just doing the last bit, we're doing the last 2 bits. And why use this method? So it does allow for a larger quantity of data to be embedded and provides a good deal of security. So this is L2SB, and it's what I used to create my prototype with. So my prototype it was created in Python. It houses the LSB method, and I've altered and changed the LSB method to encompass my L2SB method. For any further questions with the prototype, I'd be happy to answer those questions at the end. But let's move on to the testing and results. So how did I test? I used 2 measures for the testing. I did objective testing and subjective testing. For the subjective testing, I did it on participants. So I picked 10 participants and showed them 11 variations of the desert and autumn image. So this is an example of the autumn image, and you can see like this is message 1, and message 1 has 1600 bits, and this is the output of the 1600 bit one. This is the output of the 3200 bit, which is double of the 1600. This is message 2. Message 3 has 6400, and message 4 has 12800 bits. And then the other 2 incorporated messages are the MLSB max and the ML2SB max. So what I did with these different images is I showed them to 10 different participants on PowerPoint, and they would reply with a yes or a no answer. Yes meaning they saw the image corruption, and no meaning they didn't. And those results are on here in these 2 tables. This is the autumn, which is the image I just showed you, and this would be the desert, which is the one up here. I also tested objectively, which is the actual comparison between each by pixel within each image. To do this, I use an image comparison tool, and it takes both images and with the original one, original versus the encoded variation, and tracks the mean absolute error, which is the average absolute differences pixel by pixel. And those results are plotted here on this graph. So what I noticed with the subjective is that from message 1 through 4, no one could see it. From both LSB and L2SB, the image corruption rate was 0%. But why is this? So the reason that I found is the way that the human eye processes color, and how many total bits there were. So we process color with irons and cones, rods and cones within the retina. But the smaller messages made the images changed very subtly, so the color could be easily blended into one another. For example, the message 1 was only 1600 bits, and the total data capacity for the least significant bit was 300,000. And the max one, which is message 4, which is 12,800 bits, still within 300,000 bits of data capacity, 12,000 is nothing. And that's another reason why they couldn't see anything. It's because it's just the data capacity was just too large. Similarly with the L2SB, which is double the LSB, remember, it would be 600,000 for the autumn image. And with that being said, the message 4 was only 12,800. So that's a potential reason why the participants couldn't see the M1 to M4. But with the ML2SB max, which is all 600,000 out of 600,000, the participants, 40% of the participants, could see the little streaks of image corruption. With the objective testing, we have the LSB in blue and the L2SB in red. I noticed that the L2SB had a higher mean absolute error, which makes sense because instead of changing 1 bit, I'm changing 2. This brings us to our limitations. So what are the limitations in this project? So there are a couple of limitations. We have that I only tested 10 people. So I would need to test a wider range of people to get a variety of results. And same with the images. I would have wanted to have a variety of images to also get a variety of results. So this brings us to the conclusion where I noticed that the LSB and the L2SB performed really similar to each other in both subjective and objective measures. But knowing that this is a cybersecurity project, the L2SB algorithm has a chance to be used unethically, even though it was designed to be used ethically. So to reduce the risk of unethical image steganography, always pay attention to images, always download image software, and implement image steganography usage control tools. Additionally, I would also want to, with more time and resources, try to make an L2SB deciphering tool to also prevent the use of unethical L2SB. So the main takeaway for this project, it is essential to know what images are, how they work, how data can be hidden in them, and how to stay protected. Anyway, that brings us to the end of my presentation. I just would like to mention that I'm really interested in cybersecurity. I really hope to see you next year, and I'd be happy to answer any questions. Thank you.